Precalc, we are moving on to the second day of 2-3. You can find these notes on Canvas, print them out, or do them on your own paper. We're going to talk about something called the intermediate value theorem, or IVT. The intermediate value theorem, I'll read this and then I'll explain it. And hopefully by the end of the notes it'll make more sense. The intermediate value theorem basically says a function that's continuous takes on all values in between two given values. Therefore, if a function is continuous and has a function f of c, which is between f of a and f of b, then c must also be between a and b. Alright, essentially intermediate value theorem says that, like, if you have, I don't know, let's say that this point here is 2, -4, and this point here is 10, 10. Alright, and they ask you, is there a possibility that at some point you would get a y value of 6? Well, by the intermediate value theorem, it basically says, well, this function is definitely continuous, and if this point here is at 2 you have a y value of -4, and at 10 you have a y value at 10, that means that somewhere in here you definitely have to have a y value of 6, because you're going from -4 and you're ending at 10. It's continuous, so at some point you have to end up at 6. That's what intermediate value theorem is going to be all about. I'll show you with the f of a stuff. So, like, if you have a point A and f of a is some y value, let's say f of a is here. Alright, so we got a point A, f of a. And let's say we have a point B here, and the y value f of b is up here. Alright, it says in here that if there is a value f of c between f of a and f of b, so let's say that f of c is in between, it basically says, so let's say f of c is, I don't know, here. It basically says that therefore c must also be between a and b. So if you look at where the y value is, and then you go down to where the x value is, the x value is going to have to land somewhere in between a and b. Or a function can look like whatever, but that's the main gist. But the key part is it has to be continuous for this to work. So we're going to use the intermediate value theorem to determine if there's any real number that's exactly 1 less than its cube. So we want to know if there's any real number that's equal to 1 less than its cube. So we're going to cube it and subtract 1. Alright, what we want to do is we want to graph this thing, so we got to make it equal to 0. Bring the x over. We'll have x cubed minus x minus 1 equals 0. Alright, we're going to graph it on our calculator. If you go to your y equals and you graph this thing, you will see that the function is continuous. And you probably knew it was continuous before you even graphed it, because there's no vertical asymptotes or anything like that. So our function is definitely continuous. We want to know where exactly it's going to be, where this is going to be true. Alright, since it's equal to 0, alright, what you could do is you could make y equal to 0, so you could see a red line going across here, but basically we're going to be finding this x-intercept. Okay, that's the goal, is to find out what that x-intercept is. We know the x-intercept is something, 0. We just don't know what that x value is yet. Okay, that's what we're trying to find. And we can easily find it by graphing on our calculator, which we'll do in a minute. Alright, but what I'm going to do is start looking at the intermediate value theorem aspect of it. If you go to your table, alright, you might have to change some of your settings, but if you go to your table, you'll notice that we're looking for something, 0. We don't see a y value of 0 in our table, but if you do notice right here at where x is 1 and x is 2, it goes from a y value of -1 to a y value of +5. Alright, and since it's continuous, and we're dealing with intermediate value theorem, we know that somewhere between -1 and 5 we're going to hit 0. So somewhere between 1 and 2 we're going to get the answer that we need. So we know our answer is going to be somewhere between 1 and 2 based on the table. Alright, we can definitely use our calculator to find that value. You can just do second, trace, you can find the 0, number 2. Left bound, so you just go a little bit below. Right bound, you go a little bit above, and then guess. You'll get an answer of 1.325. Okay, so we know that x is 1.325, but the key part is the intermediate value theorem and explaining it. All right, so basically our explanation is that since there is a continuous function, and the function changes signs between x equals 1, b slash w is between x equals 1 and x equals 2, there must be a 0 in between these two values. All right, again, going back to the table. All right, if you go to your table, again, between 1 and 2, we went from -1 and 5. So somewhere between -1 and 5, you're going to eventually hit 0. And we hit that 0 at 1.325. Okay. Let's look at the next ones. So we're going to sketch some graphs. A function that has no limit at x equals 3. We have the left-hand limit, we have the right-hand limit. You can see they're different. That's why there is no limit, because they're not equal to each other. And f of 3 has to equal 3. You have a lot of leeway with these. You do not have to draw them exactly the way that I'm drawing them. But we do know f of 3 has to equal 3, so that's definitely a requirement. F of 3 has to equal 3. Other than that, let's see, the right-hand limit, we'll just deal with the right hand. As we approach 3 from the right, it should approach 3. Okay, so it should approach this point. So coming from the right, however you want to draw that is fine. But as we come from the right, we should approach a y value of 3. Check, that's done. Then we have the left-hand limit. As we approach 3 from the left, we should be equaling or getting closer to -2. So I'm going to need some kind of a point here. And so that when I'm coming from the left side, I'm getting closer and closer to a y value of -2. Now, since f of 3 is equal to 3 here, I can't have a closed circle here. I have to have an open circle here. All right, so something like this. And what you'd have on the left side and the right side, you could do whatever you want. But these points are a necessity. All right, and you can try it out. From the left, as we approach 3, we get -2, closer and closer to that y value. And as we approach 3 from the left, we get closer and closer to that y value of 3. Check. All right, B. A function is continuous over all x's except x equals 2. Removable discontinuity, which is a hole. All right, so it's continuous everywhere except at x equals 2. All right, and again, it doesn't matter what the y value is. It doesn't even tell you. So whatever you want, but there should be a hole at x equals 2. So I'm just going to make a hole here at x equals 2. And then whatever you decide to draw for the rest of it, draw for the rest of it. But it should be continuous everywhere but at that hole. All right, so not too bad. Let's see. Letter C. All right, f of x is decreasing for x greater than 3, increasing for x is less than 3. Think of this as like slope, okay? So decreasing, it should be going down from left to right. And increasing, it should be going up from left to right. Okay? Let's see, and there's no limit at x equals 3. All right, so it's got to have a different left-hand limit versus a right-hand limit. So it's decreasing at x is greater than 3. So let's get x is greater than 3. You can put whatever y value you want. All right, I'm just going to make a hole. You can do whatever you'd like. You can make it a filled closed circle. It's got to decrease as we go to the right of 3. So it's got to go down. Notice this is definitely decreasing. And then for x is less than 3, so everything over here, it should be going up from left to right. And again, you can put whatever point you'd like at 3. You can have an open circle or a closed circle here. But it should be going up from left to right. So it's increasing as we get closer and closer to 3 from the left. And then decreasing as we go to the right. And there's no limit at x equals 3. Yeah, as long as the left-hand limit and the right-hand limit are different, this one's approaching something positive, this one's approaching something negative, we can even give it some points. Maybe make that 3, 2, and this 3, -1. But yeah, you can see that they're approaching different values. So there is no limit. And that would make up all of the requirements. For number 3, going to be doing a problem where we have to find a so that the function's continuous. If you look at 4 minus x squared, that piece we know for sure is continuous. It's just going to be some kind of a parabola. There's no vertical asymptotes, no holes. Same thing with this ax squared minus 1. No matter what a is just a number, it's still going to be a parabola. It's going to be continuous. The only place where this thing could not be continuous is right here where like x is equal to -1. So what I'm going to do is I'm going to let x equal -1 and plug it into the top piece. When I plug it into the top piece, I know that it's technically not equal to it, but this will come in handy in a second. When we do this, we're going to get 4 minus -1 squared. You're going to get 3. All right, so in this section of the graph, we're going to have a hole at -1, 3 because it's not equal to it. What we want to do is we want to fill in that hole, okay? So what we want to do is we want to have the same kind of outcome. What we're going to do is we're going to set this piece equal to 3 so that it fills in that gap. So we're going to do ax squared minus 1 equals 3. All right? And we already know what x is. X has to be -1. So I'm going to make x -1. And again, it has to equal 3 because we want to fill in that hole. We want x to be -1 and we want the y value to be 3. And so now we can find out what our a value is. When we plug this in, we're going to get a minus 1 equals 3. Add the 1, you're going to get a equals 4. And so now when you plug in -1 with the a being a 4, you'll create a point at -1, 3, which fills in the hole. For number 4, we've got the function f is continuous for all real numbers x. So this is our continuous function. Explain why there must be a value r. So r is between -5 and -2, such that f of r is equal to 8. The function is graphed below. Okay, so if you look at this graph here, all right, we can see that at f of -2, it's equal to 4. And f of -5, it's equal to 11. All right, so we know it's continuous. We have to explain how we know that at some point f of r is equal to 8. Well, you can even see it from the graph. You know, at some point, some r value, this graph does eventually reach a y value of 8. We just need to prove it. This is where the intermediate value theorem comes in. It basically says, since f is continuous, all right, and r is between -2 and -5, and f of -2 is equal to 4, f of -5 is equal to 11, all right, because of that, by the intermediate value theorem, I'm just going to put IVT, the function must take on every value in between, all right, which means, so if we're starting here at, eventually we go from 4 to 11, well, you're going to end up hitting all of those values between 4 and 11, meaning you'll hit 5, 6, 7, 8, 9, 8 is the one we need. We're definitely going to hit that. In between, which means that eventually f of r will equal 8. Okay, so that's just the intermediate value theorem and kind of explaining it. We don't actually have to find the r value, it's just explaining how we know that eventually f of r will equal 8. And that's it for intermediate value theorem.